same model. Okay. Now, the first method is model response spectrum method. Do you remember here I told you that we need model analysis and response spectrum. So what we need to do is to do model analysis, and then after that we define the response spectrum. Here is, but of course, in order to build the math matrix, you have to give the math source to the structure. And I showed you where to find. This is the combination. If you find this coefficient, you will have these values. One for self-weight, one for slab, one for super dead, 0.25 for live, it's reduced, and no snow. This is the math. Okay? How to do that? Click define math source, modify. Click define math source. Let's keep it, we'll just modify. We'll not build new. We call math source. But look, we cannot modify. What's the problem? We cannot insert anything because we have run the software. If the software is run, we have first to unrun in order to modify. Again, math source. Okay, sorry guys. Then define math source, modify, call it math source, and then you have to, you have to click on this one, specified load pattern. Otherwise, it will take self-mass and additional mass by itself. Since we are not sure how this works, we just define our own self-weight 1. And you have to unclick the first one, okay? We don't want it, otherwise it takes more masses. All dead loads by 1. Live load we set 0.25. You can stop here or you can insert the snow and put 0. Oh, sorry. Okay, live also 0.24. So we have our mass source, okay? Okay. I will show you where this one is taken into account later. This step is necessary for all types of analysis, not only for model analysis, spectrum analysis. Okay. But I will give you also the mode. Yeah, but it's the same one in the slide because I'm applying the same example. It's fine. Okay. Okay, so we define the mass source. The next step to do is to perform the model analysis. How to do the model analysis? It's very, very easy, okay? We define load case. The model case is usually defined as default by the program. So we just modify it. We don't need to define from scratch. We will use eigenvectors. Okay, you can also use something called Ritz vector, which gives a better result. However, since we are doing linear analysis, both methods will yield the same value. So we are okay with eigen. This one we all know. And maximum mode, we'll keep it as 12 because we have very regular, very small buildings. I don't think we'll need more than 12 modes. We don't need to change anything. And here is the mass source that we defined, mass source. It will use it for math matrix. Number of modes should satisfy the minimum mass participation. Now we will check the mass participation later. Let's see the result of the model analysis. Just let's run it. Although we didn't finish the method one, but let's run it. Okay. Now, we click on the deformed shape, but not the envelope. Do you remember we put envelope at first? Now we don't want envelope. We want the model results. Mode number 1. Okay, you can select whatever mode you want from here or from outside. Because look, I clicked on this one, so the result is here. But you can see it in 3D, so you click on this window and then you do the same thing. Because it differentiates between windows. You can see result on one window and another result on the other window. So apply. Is familiar? Yeah, this is the first mode. This is the most stiffest direction, right? The period is 0.6. You can read it from here. You can change the mode from 1 to 2 by clicking on this one. So look, we have the second mode, 0.63. Let's see. All right. Here's what we expect. And third one, it's rotation, right? And you can go ahead and see all modes. How do we know that the number of modes is okay? We don't need to insert more modes. We need to check the mass participation. How do we do that? And I already I've written that in the slides. You can display here, show tables. All results can be obtained from here, show tables. Okay? And then we go to structure, output, model information, and then model participating mass ratio. Here is not enough. You have to select, you have to make sure the load that you are interested in are selected. Okay, so we have all these loads. Here model, load case, model. Make sure don't put another load case or it will give you wrong result. So how to know? How to know what is the value of the mass participation? You have to differentiate between direction. Let's see the X direction. The second mode, we have 89%. So if you are working with the Italian code, we need 85, right? It's already okay, so we keep. But if you are working with the Eurocode, you need 90%. So you have to sum this one with this one, with this one, with this one. If they are more than 90%, you are okay. If they are not more than 90%, you have to increase the number of modes. And yeah, you have to check that for X, for Y, for Z. You can change in the same way. Define, load cases, and then model, and then here you increase. Okay, guys? This is how we do the model analysis. We are sure it's correct, right? Because it gives logical result. So what's the next step after the model analysis? But before I show you the next slide, I want to remind you of this one. We said we need model analysis and we also need response spectrum. So now I expect to define the response spectrum. How to define response spectrum? It's very easy using SAP because it has all the codes of all the countries. So it's just with a few clicks you have your response spectrums. Define functions and response spectrum. Define function and response spectrum. And then we put NTC, right? You have the NTC in Italy. Italian NTC 2008, and a new function. And here we go. You have multiple, all right, SAP asks for coordinate system, for coordinate for the city. In this file, I put you seismic information. We are studying the city of Cassino. It has this coordinate. So in the lateral, 41.484. Lateral here, 41.484. Well, it's a bit different than that because they work with degree and stuff in the coordinate system, but it doesn't really matter. You see here degree, and so we'll just put a comma. And the longitudinal, 13.957. Look, you got a new one. Now, what limit state we will work on? Usually you have to perform two. One for damage and one for life safety, SLV. But for the purpose of this example, we'll define only one, SLD. A usage class, it's written in the document, it is, well, reference life VR. And you know that reference life equal to nominal life times class. Okay, here we'll put class 2. In this table, class 2 means 1 occupancy factor. But here I give you the final number. Reference life is 50. In SAP, you have to insert the nominal life, and then you have to insert class, and it computes. Nominal life is 50, and the usage class is 2. Soil type, let's check it again, it's C. And topography is T1. Right, guys? And here, so we have the behavior Q factor. What we are working on is SLD. Do we need to include any Q? We don't need to include any Q. We keep it as 1. Because if you include the Q factor, the values in the spectrum will decrease in order to account for the non-linearity in the structure. However, when we do SLD damage, we assume that our structure will be linear. So we don't need to increase the Q. Now for the other limit state, SLV, we need to insert another one. You compute it. All right? So we'll keep it. I will call it SLD. Here it is. Okay, create one for SLD and one for SLV. Remember to insert Q factor for SLV. Whenever you want to define new force response spectrum, you need to define load case for it, as we did. This is just not for you. You can read it. Now we inserted the function, but we need to assign load case. How do we do that? Define load case, if you follow. Add new, and then if you remember this one, we used it when we defined the forces, the model case, right? But now we'll use for the response spectrum because everything needs load case. So change load case type to response spectrum. In the model, it was static, now response spectrum. It's updated. You can here set whatever combination you want as RSS or CQC. You may be familiar with those. We'll keep it. Or you can say CQC, it's okay. Okay, and here's the important thing, load type. Here's the important thing. We apply as acceleration load name in the U1 direction. U1 means in the X direction. So we are only applying in the X direction, not in the Y. Function SLD, the one we defined, and scale factor. You know that the value inside the response spectrum are in terms of G. So you might have heard of like AG equals 0.25 G. So they are in terms of G. However, if you want the real values, you have to multiply those values by 9.81. And we'll do that here. You click add, and you have it. Because the ground acceleration is in terms of G. Nothing else here. Everything is fine. We didn't give it a name. Let's change the name SLD. Or RS, response spectrum SLD. Okay, guys. So, we have the model analysis, we have the response spectrum. I think we are ready to do the analysis. Model response spectrum analysis. Results, you can run the analysis and see the results. We will see that later how to show the result, but I have already shown you. What is the case, the load case? This one. But since it's linear, let's run them all. They will not take time. Of course, you can click on that shortcut and you can put RS and then you can apply. Okay, and here you have your deformed shape. You can see also your forces. Of course. So yeah, before we see the forces, let's show you how to magnify the deformation. I remember I did that once. Maybe that was another software. So I'm not sure. Maybe that was another software I knew of, but here's yeah. It's not very important, but I think by default it gives you it shows you deformation, so you can you can see it. You can see that you have deformation, so it won't be like very small. It adjusts accordingly. So also the results, guys. Using this, you can do this all the analysis, and then you can compare results, because you know we are applying all analysis to the same model. Moment, it's very close to the moment we got before. Remember when we shown the moment? But yeah, all right. But here we are more interested in the seismic actions. So in the shear, right? Or in the moment, in the other moment. Okay. It's getting slow. Also axial forces, shear. And so on. So we are done with this method. So the other method, second method, is the equivalent lateral force method. I would like also to remind you that here we only need response spectrum, because in order to find your base shear, you will have the formula in which you have to use the response spectrum. Okay? But first, we need to define, the first thing we do is to define the center of masses of our building, okay, in order to apply the load on these at these points. So from your first let's unlock it because we need to modify. Let's see. As first guess, where do you think the center of mass will be? It will be in the center, right? Because our building is regular, so it will be along this axis and this axis. So the intersection between this and that one. But here we don't have a node, in fact. So we need to add node here. How to do that? There are two ways. The first one is to divide this beam into two, which we'll not do now because it's not general. Because sometimes the center of mass is not located on the beam, so there's nothing to divide. And the second method is to build new grid line that intersect at this point. So I've written that here as well. Okay, how to build the grid line? Do you remember? It's define and coordinate grid line. And the same system we modify. Now we need to add. In the x direction, we need to add one here. What's the coordinate? It's 4 point. It's in the middle of 14.5, right? 14.5 over 2. It's 7.25. We add, we insert 7.25. You have to click enter again. So we have one in the middle. Okay? We only insert in the x direction because here we have the z. So in fact, we didn't build only one grid. We built one grid in the x direction along all the stories. Let's see it, and here it is. Here's something very important that so this is our grid line. You know, I can click on the point, right? I can click on the point, but this is not a node. This is just an intersection. So if you apply any load here, it will not be taken into account when the model is run. You have to insert node. How to do that? You have to click. No, you don't have to click, but you have to draw node. Like you draw frame, like you draw area, you have to draw node as well. Draw a special node, a joint. The grid, like we did in the first place, define, and then coordinate system. You just modify, you don't build something new. Okay, and then you add here, you add something, new line appears. Because the grid that we want to add is here, right? Because we want to intersection between this one and this one. And we already have this beam. So we have the intersection. So it's in the x direction, right? This direction, orthogonal. So you add it and you define the coordinate. It's 7.25 because it's the middle of the x direction. Okay? So let's continue. As I said, we have to draw joints. Draw special joint. Mistake. We go back in this, using this, and we assign one here, one here, one here. Now, do you remember when we defined the diaphragm? We selected all the nodes on the same story, on the same floor, and we assigned the diaphragm. This is what we did. Now we inserted new joint. So what we need to do is to assign diaphragm to this node as well. Otherwise, it will behave differently from the other nodes. We click, and also I've written that here. So don't need to worry. on the third story, I clicked on the node and then assign, join, constraint, and because we have already defined it, we will have the diaphragm. So which one among these? The node is on the third floor, so we click on the diaphragm 3, apply. Okay, it's unselected automatically, so you don't unselect, you select the second one. And look, all the nodes that have the same diaphragm have the same color. Okay, so this one is just in order to check. Look, green, 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 all of them. Now second one, you click and you assign diaphragm 2. The green ones move to the second floor, so you can have idea that you are doing okay. And diaphragm 1, and you are okay. So we inserted the node. So we finished this center of mass. We define the center of masses. We move and we apply the force and the moment. Okay, but we did not define the force and the moment. Step by step. Whenever you want to define force, you need to define load pattern. This is what we did, and this is what we are going to do now. Create a load pattern for the force and the load pattern for the moment. For each direction. So how many? 2 times 2 is 4. So define load pattern fx. Always load pattern. Whatever you want to do with load, you have to define load pattern. I will not put that. Let's see what I put here. I put pattern life. So I'll keep it the same. In more. Pattern life fx, no multiplier. Fy, my, mx, and my. Guys, if you are working on 2 limit states, you need to define 2. 2 for each limit state. You have to define 4. Fx, Fy, Mx, My. Okay, but in this case we are working only on 1 limit state, so 4 are enough. So we continue here. Define load pattern. For example, if you are studying, this is not important. This example we will study only SLD. I already said that. A load case for each load pattern will be automatically created. Define. Let's check it. How to check load cases? Define load cases. You see, we have the 4 here. Go and check. And here's a screenshot. We go ahead, and now we need to apply the forces. In this table, I have once computed them. However, I'm not really sure about the real values. You can do that by your own. However, in this example, I will use those values. If you see, I have different stories, and I have different forces. Why we don't see here Fx and Fy? Because in this method, Fx equal to Fy. You know, because the formula of the base shear does not depend on the direction or the stiffness, it depends on the height, and we have same height. So these values will be used for both directions, but the eccentricity will be different because each value has different lengths, so different eccentricity, and consequently different moment. Mx, accidental moment, it's called Mx and My. Let's see how to assign them. So here we are, okay, all right, you can see characteristic, but it's not important, it will not change anything. Always save, don't forget. So I like this view, let's keep it. This node, or let's start with the first story. On this node, apply the loads and the moment at the center of mass of the different story level. I just want to zoom so I can see the values. Okay, how to assign force? We have already seen that. Using assign. We want to assign on joint Load or frame or what? Joint. Yes. No. Yeah. Right. Thank you. Yeah. Okay. You can click on that to clear, or you can click somewhere else. So we click again. One. Assign. Joint load. Joint load means force, moment, whatever. So Fx in the x direction, how much is it? 84.81. 84.81. It's fine. Apply. And then you can here use the previous selection. And the same joint will be clicked on. Okay, you see it? Fy. Okay, now the same value will be applied in the y direction. Here, put here. It's easy. Now mx. So around which axis, guys? The moment. X, Y, or Z? Because it's torsion around the slab, so it's around that axis. Okay, here we insert the value. So it's 22.9. We did not select the node. We can select it now. And we move to the my. How much? 49.19. my. You select the node again, and you click OK. Right? And then we do that for the second node. Fx 0 here. 152. Do you see it? Previous selection. Fy, same value. It's not important here because we are defining something new, so it will not replace anything. It will replace 0. Okay, and then mx 41.14. You click on the node, and the last one, how much? 88.38. We click on that. And then the last one, I'll do it quickly, Fx 184.1, no, not here, 184.1, Fy, same value, we just copy to the y direction, and here we put 0, but we also click on the node, which I always forget, mx 49.71, don't forget to remove this one. And the last force. Now guys, when I repeat this example, you will understand it better, okay? Because you will have time to understand better. However, you will have all the material needed. So this is the last force. We applied Fx, Fy, Mx, and My to the 3 stories. We go out. So we are done with applying the force and the moment. Now the next step is the load combinations. Do you remember this table? So we have 16. We eliminated 8 of them. We are left with only 8 combinations, which are in the black color. This is only for one direction because we are studying X direction. Okay, don't forget that. If you want to study another direction, then you have to do everything we did for the other direction. Now, We have talked a little bit about load combinations, so we are going to do the same thing. And also here written, combine all possible cases. Note, some of the cases can be easily cancelled. Blah, blah, blah. This is what I said. And here is the figure that you get. Anyway, let's do that. Combinations, define load combinations. Now, forget about those. We'll not use them. Add new combination. This is combo 1. Keep it. Okay, so let's see the table. So let's apply these load combinations. The first one is 1fx plus 0.3 fy, don't forget to add, fy 0.3, and then mx 1, and then my 0.3. You've got your combination built. Second one, I will build only 2. I will not build the 8 combination, just I'm giving you an idea about that. Now 1, 0.3 minus 1 minus 1. The combination is critical when both moment share the same sign. See here, same sign, same sign, same sign. Here different, so it's green, we eliminate it. So minus and minus. Fx multiplied by 1 fy 0.3 mx minus 1 my minus 0.3. And you continue in this way and you get 8 combinations. Yeah, thank you. Modify, not add. Okay, so I assume we suppose that we have built all 8 combinations for the x direction and for one limit state. So after combination, and this is what you get and what we really did. Now when you have the 8 combination, what are you going to do with them? You are going to see the result of each combination alone? No. You have to do the envelope as well. Now envelope, and you this method too, okay? Here we change load combination type from linear add to envelope. The same thing we did before when we combined ULS1 and ULS2. Make sure you select combination 1 and combination 2. Add. Okay, you can carry on until the 8. You get 8 combination. And of course, if you study the y direction, you will have another 8. Here you will do envelope for the 16 combination. If you study two directions, but you don't put the envelope, the combination of the 2 limit state together. If you have SLD and SLV, you do one envelope for SLD, one envelope for SLV, because SLV you will use it for design, SLD will use it for deflection and interstory drift, so they cannot be put together. And okay, and you continue, guys. So this is the method. We just click on the run and we run the analysis and we can see the result in the very same way. Nothing is different. Okay? So now we have applied 2 methods, 2 linear methods. This one, which needed model analysis, and this one, which didn't need model analysis. We needed forces that we use the response spectrum to get them. Okay? Let's move to the nonlinear method, and this is very important and it's used very much in the research. Also, along with the nonlinear time history analysis, which we don't have time to explain today. But pushover is very powerful, and it's not time consuming. It doesn't need much time to be performed. Just less than 1 minute. Okay? Let's do that. So, pushover analysis. Now, in order to account for the non-linearity in the system, we have to do something. In the linear method, what we did is that we defined Q value for the response spectrum. But in this way, we'll not do that. We'll define plastic hinges. And the software can do that as well. So this is the first step. Define plastic hinges. How to do that is you can select all beams. You have to select first all beams. Now how to select all beams? We are not going over the beams and click one by one. There is the select command here. Select, and you don't need to put them in a group because you can select according to the property. So select and select again, and then by property, and then material or frame section. In this way we pick frame section. Now, we want to select beams, right? Because plastic hinges for beams are different than those for columns. We can do that together because in the columns, we account for M2, M3, and all of the axial force in order to build the curve of the. For the beams, we don't want that. It's much simpler. We only generate plastic hinges for M2 and M3 for these two directions because we assume that there is not much axial force in the beam, so we don't take that into account. So we select the beams, select. See, all the beams in the models are selected. Now we need to assign plastic hinges. Assign frame, here's frame, and then hinges. Here's hinges. You have this new window. Computer is getting slow. Okay. Here, add hinge at relative distance 0. So the beginning of each beam, the start point of each beam. For each element, you have to define two plastic hinges, one at 0, one at 1. Some people don't put 0, they put 0.05 because they assume at location equal to 0, no plastic hinge will be generated. Just a few centimeters after that. Okay, but here we'll put 0, add hinge. Easily, we will follow FEMA 356. And then we have steel or concrete, beams or column, beams. Okay, it's enough to put M3. We don't need to put M2. M3 is the moment in plane. Okay, so it's enough to put here M3. We don't need to generate moment plastic in the M2 because the beam will not deflect in that direction. Okay. All right. Are local coordinate for the beam. For each beam, it has its own local coordinate. M3 is the moment around the not torsional M3. No, it's the in-plane moment. It's the normal moment that usually applied to beams. So since this is the primary moment, we say we insert plastic hinge in this direction, around this axis. So if the beam is deflected more than its what can stand, plastic hinge will be generated. Why we don't put M2? We can generate also for M2, but the problem is that we will need much more time, especially if you have big building or complex building. It will need us very long time in order to run the analysis. It might take, guys, really, especially if you are doing nonlinear time history analysis, it takes days. It took me 15 days in one of my project just to run one analysis. So you will be really interested in saving some time in these very small details. So in this way, we will put only for M3. And also same thing for distance 1. M3, everything is okay, so we go. Apply. We see plastic hinges information for all the beams at the beginning and at the end. We do that. You can check the plastic hinges, guys, also. And we will see that after a while. Now also for the columns, right? Now select, and now properties, frame section as well. But now we will select the columns, not the beams. So not by one by one, we can select both of them. You can click on control and then second one. All right? In this way, you apply for both, you select both. So we have all columns selected. In the same way, we can say assign, join, not join, frame, hinges, also at 0 distance, and at distance 1. Add hinge, FEMA as well, but not beam, concrete column. You see it? We have different options. We'll use this one. We'll take into account also the axial and the M2 and the M3, because you don't want your column, if you have earthquake in the X direction, it will bend in this way. If you have in the Y direction, it will bend in this way. So you need the plastic hinge in both directions. But also your building is can have also torsional, and we see in the third mode it will have torsion. So your column can have torsional as well. All right, and because it supports axial forces, you have to include P, because you know the value of P, the axial forces, affect the maximum moment that can be stand by the column. So P, M2, M3. And also at 1 hinge, here they don't change, so it's easy, and then apply. Okay, so we have plastic hinge for all our beams and all our columns. Now, in order to... No. Okay. Do the same for the column, P, M2, M3. You can see the plastic hinges that you created and verify with your calculation. You can do calculation, manual calculation, and then you can check if you feel like you are not very certain about the values given by the software. How to do that? By define, because plastic hinges can be defined manually. Okay, define section properties, and then hinge properties. We don't see anything. Why? Because we didn't click on the show generated property. Yeah. Okay, some of them are for the column, some of them of the beam are for the beam. Then modify again. This is for the column. I don't want to see one of the column. Okay, this is one plastic hinge for the beam. I think you have seen something like that. When it reaches this this amount of force, plastic hinge is generated. Okay, little bit of stiffness, and then the force drop. Okay, and then those are the value that you can generate. Anyway, however, I will not go in details because the values given by the software are really reliable, and I've tried that. Okay, so plastic hinges are generated. Now we need to define the pushover curve, the pushover load, sorry. And as I told you, everything concerning the load, you need to define a load pattern for it. So let's do what we have done 3 or 4 times. Load pattern. Now, load pattern name, we will name it push. I told you there's two patterns for the pushover load. It can be uniform, and it can be also triangular, according to Eurocode. But we'll use in this way, we'll use only the uniform, just to simplify, as we don't have time. However, it won't be different from the triangular. You push uniform. Okay, and type pattern life. However, type will not really matter unless you are using the design provided by the software itself. Then the type will matter because software will assign the coefficient according to the code of your country. Okay, this is more advanced. We will not use that. Push uniform. Okay, and then we carry on, we continue. Push over load shape. Okay, now since we have defined the load pattern, we need to assign the load, the uniform load. So we'll assign load pushing the building from one side to another. We are working on the X direction. If you are working on the Y direction, you have to do that for the other direction as well. Okay, so if you want to remove this mess, you can just click on the show and deform chain. But first on the window. So uniform, I will push the building from this side. Okay, all the nodes of this side. And then we will assign joint load force. Now, make sure you select the load pattern that you define, not something else. Push uniform. So it's in the X direction, it's here. We put, what's the value that you would like to put? Whatever value you want. However, I'm used to put 1. Okay. What's important here? The proportionality between the forces at the different story. If you apply 1, 1, 1, then all of them are equal. For example, if you apply triangular, it can be 1, I don't know, 0.6, 0.3. But it also can be 10, 6, and 3. The important thing is the proportionality between them, not the value. Okay?
But the concentrated forces are related by considering the length of the vertical element, the distributed load on the selected area.
Okay. No, I apply a point load at the joint. Okay, this is very enough for in our purpose, because you want to apply distributed along the columns. You want to do that? You can. You want to apply distributed load along the columns? You could do that as well. But in my case, I apply joint load because I have already defined diaphragm for the joint. So the joint will more or less move together. So it's not really important. Okay, but in your case, it gives more exact results. It's okay, it's not a problem. Here, guys, before I click, I forgot that there is moment. How to solve that? You repeat that, you put 0, and then you put replace. In this way, you can remove the moment that I generated by mistake. You know, because there was value here, and I forgot to remove. Previous selection here is important. Look, the nodes are selected again. Apply, and the moment are gone. Let's continue here. If your load pattern is triangular, you have to apply different load value at the different story level. The load value are proportional to the story mass and the story height. So the triangular load will be only triangular if the masses of the all story are equal and if the height is constant. You know how to compute proportionally to the mass, and it's approximately the same formula we use in the base shear distribution. Z times M over sigma Z times M. Okay? This is in case of triangular. We will not do that here. We are just a few slides ahead to go. Push over load case. It's necessary to change the dead load, as this is important. Whenever you need to do nonlinear analysis, you have to change the dead load case from linear to nonlinear. How we do that is from define load case and that. See, it's linear static because in our linear analysis we use it as linear. We don't need it nonlinear. You just change to nonlinear. As easy as is. Modify, check nonlinear, and okay, we have it nonlinear now. A new load case will automatically be generated after you have blah blah blah. I think this one should be, I already included somewhere. Let's continue. Analysis type. Okay, yeah. Do you remember, guys, that when we generated the load pattern of push uniform, we didn't go here, right? But we need to modify because we are doing nonlinear analysis, but still linear. So in the same way we did with that load, we need to adjust something in the push uniform. Okay? So we defined the pattern, and then we applied the load, and then we modified that load case and the push uniform. Now, push over, check, define, case, can change planning. Okay, here is written what we have to do. Analysis type, nonlinear. And then we have to check, continue from the state at the end of the nonlinear case that. Here. You know, if we didn't put that as nonlinear, that will not show here. It was necessary that we change that load to nonlinear in order to see it in this case. So now the software, what will do is that it will apply the dead load, and after the application of that load, it will start pushing. Because this is the reality. We have that load, and then we do the pushover. Okay, and then load type. Okay, and here load type, this one, is load pattern. And load name pushover, and it's there by default. If it's not there, you have to modify or you have to add. Okay? And you have the screenshot here, the same one we are doing, so you can refer to it later. But here we have to change some parameters. We have to define how much we should push, what joint we will measure. Okay, now we continue. Click on the load application, which is this one. We want displacement control. Use monitor displacement. Usually the top of the roof, how much will it display? I don't know, a few centimeters. But if you have big displacement, you can increase this value. You can put it 1 meter. So you keep pushing until the building reach 1 meter. But if you have plastic hinges, once you have the plastic hinges in all your columns, then the analysis starts. And your building fails, collapse. I will keep it at 0.38. All right, and then we have to set the joint. Which joint you will measure? The joint at the roof. How to know that? Easily. For example, because we put diaphragm, any node, this one, it's labeled 59. So again, we go to the same place. It is pushover. We are almost there, okay? How much was it? 59. And nonlinear parameter will not do anything. Final state, we need multiple states, up to 100. So 100 steps. Okay, and in this way you have defined your load, your pushover. Okay, and here, I'm almost there. You run your model. This is the third method, guys. And then we need to see what? The pushover curve. This is why we are doing that. How to see the curve? I wrote that here also, and in display but we will not go to table, we'll go to show static pushover curve. It has special command. Here it is. And if you want to see the performance point according to the ATC capacity spectrum, you just have to click this one. And it gives you all your spectrum and also your pushover curve. But you can see that this curve is different than this one. Why? Because here it's in terms of displacement, spectral displacement, and spectral acceleration. Okay, not displacement and force, spectral displacement and spectral acceleration. And here is your performance point in the SLD. Here is your performance point, SLV. Here, and they are written here also, 3 performance points. You can read about what is performance point in order to understand. This is very important. But here's how to do it. Okay, guys. Yeah, the curve, and just 1 second, we can see the results of the pushover curve, and we can see the plastic hinge being generated. This is the last thing. Pushover starts from step 0. At step 1, we have this pink. Pink means nothing. It's no damage. It's just in the beginning. We can change from one step to another. Look, more pink. Oh, it's blue. Blue is in this field. It's still less than SL, LS. It's still in the operational. Then you move ahead, and more plastic hinges.